So this is how the MOSFET is available in the market. It has three terminals. From left side the first terminal is gate, after that we have drain terminal, and after that we have source terminal. So let's understand the MOSFET as an engineer. Hello friends, my name is Akshans and welcome to CADDD Academy. In this lecture we will study the metal oxide semiconductor field effect transistor, which is generally called as MOSFET. We will understand the working of the MOSFET in this lecture. So first of all, I am drawing a diagram which will give you the brief idea how the MOSFET is constructed and how it is made and how it is working. We will see all these things in the lecture. So this is metal oxide semiconductor. Why it is called metal oxide semiconductor? Because first of all we have a layer of metal, after that we have a layer of silicon oxide, and after that we have a semiconductor. So basically silicon oxide layer is sandwiched between metal and the semiconductor. So I'm drawing a diagram and from there this will be very clear. So I'm drawing a 3D diagram here, and that will give you a brief idea about how the MOSFET is made and how it is gonna work. So the above layer is what? Metal, and the dashed layer where I have made a shaded portion, and that is what? Silicon oxide. Now I'm drawing the base of the metal oxide semiconductor field effect transistor, basically MOSFET. This small portion is called as source, and at this side also we have a same small portion, and we will call that as drain. A terminal taken out from the metal is called as gate terminal. So we have got three terminals. First one is gate, second one is source, and the third one is drain. And another fourth terminal is also there in the MOSFET, and that is what? Body terminal. So here the substrate is what? P-type substrate, because here we are talking about the N-channel MOSFET. And this is the fourth terminal, which is body. So at the top we have a metal, and after that we have a silicon oxide layer. Below the silicon oxide layer all the things are semiconductor. Now we have a metal at the top, okay, this one. Then we have a silicon oxide layer, this one. And then we have a semiconductor, okay. And this metal and the semiconductor is conducting material, okay. We have a silicon oxide layer, which is what? Insulating material, okay. So these three things are forming a capacitor, and we call that capacitor as MOSCAP, okay, MOSFET's capacitor. Now we are moving to the working of the MOSFET. Now I am taking a front or back view of the above diagram. So for the better understanding, we are taking back view. So I'm drawing a back view here. So this one is metal, and after that we have a silicon oxide layer. And then the semiconductor part. So below the silicon oxide layer we have all the things that are what? Semiconductor. So this terminal is drain and this terminal is what? Source terminal. Okay, this one is gate. We have seen this before. So here we are studying about the n-channel MOSFET. Okay, so in n-channel MOSFET what happens? Source and the drains are n plus region. What is the meaning of n plus region? N plus region means the semiconductor which is highly doped with the phosphorus atom. Okay, when we dope the intrinsic semiconductor with the phosphorus atom, then we get the n-type semiconductor. Okay, when we use large number of phosphorus atom to dope the intrinsic semiconductor, then we get what? N plus region. Okay, substrate is what? P minus region. So in P minus region what happens there? We doped with the boron atoms. Okay, to get the semiconductor of P type we dope it with the boron atom, and to get the N type semiconductor we dope the intrinsic semiconductor with the phosphorus atom. So here for N plus region we are using a large number of phosphorus atom to dope the limited amount of this intrinsic semiconductor, and to get the P minus substrate we use boron atom, and no, we are not using a large amount of boron atom as we use the large amount of phosphorus atom to get the N plus region. So here we are making a P minus region. So for P minus region we are using a small amount of boron atom. We are doping the intrinsic semiconductor with a small amount of boron atom, and we are getting what? P minus substrate. Okay, and we have a terminal which is what? Body terminal. Now, except the gate terminal, we will apply the 0 volt to the all other 3 terminals. Okay, so source, drain and the body terminal, we will apply the 0 volt there, or also we will connect the source, drain and the body terminal to the ground. So at the gate terminal what we will do is we will apply the voltage, and that voltage is what? VG. Okay, let's say we have a VGS voltage. So VGS is what? VG minus VS. Okay, and the source voltage is what? 0, because we have grounded the source terminals. So VGS is what? Just VG. Okay, so this becomes VGS. Now I'm taking a case and we will call that case as case 1. Now I am drawing again the same diagram. Again this is what? N plus region. This is what? N plus region, because this is N channel MOSFET. Now we have P minus substrate here. Okay, here the gate terminal. I'm not writing the source and the drain terminal because that is grounded here and we don't have work of that anymore while understanding the working of the MOSFET. So in case 1 what we are saying is that the voltage VGS is what? Negative voltage. Okay, this VGS is what? Negative. In the other sense we can say that VGS is what? Less than 0. So how we will get the less than 0 voltage? Just reverse the polarity of the voltage source at the gate terminal. Now one more thing which you should know, that the electric field is always from higher potential to the lower side. Okay, to the lower potential. So now we have grounded the body terminal. At the body terminal we have 0 volt, and at the gate terminal we have less than 0 volt. So this will be at body will be at higher potential and the gate will be at lower potential. So the electric field's direction will be as the arrow shown here, like from downwards to upward. Electric fields will be upward in the direction. So due to this electric field, what will happen here, that the holes from the P minus region will be attracted towards the lower potential. Okay, so listen this thing again, that holes from the P minus region will be attracted towards the lower potential, because high potential is positive here, okay, with respect to what, lower potential. So lower potential here is negative for the holes, okay. So holes is attracted towards the lower potential. So I'm taking a small segment here from here to here, okay. This is what forming diode here, okay. Like this one is what, N plus region here. After that we have a P plus region. Why it is P plus? Because we have a large number of holes in that region. So first we had N plus region, after that we have P plus region because of accumulation of holes. And after that again we have N plus region. First of all we have a N plus region, after that we have P plus, and again we have P plus, then N plus junction. So this is forming a two diodes back to back, as these are connected. And we know that diode is unidirectional. Unidirectional means it allows the current only in one direction. So the net current through the branch will be 0. So as the second diode will allow the current in right side direction and the first diode will allow the current in left side direction, then the net current will be 0. So this is the first case, and in this first case we have MOSFET in off condition. And this first case is called as the accumulation mode of the MOSFET. Now we are done with the case 1 and I am taking the next case, which is what, case 2 here. And in this case 2, what will happen, that VGS will be greater than 0 but not large greater than 0, okay, not largely greater than 0. It will be a small positive value. So again I'm drawing that view. This is metal. This is what the silicon oxide layer, and the semiconductor part below of it. This is what, N plus region. So drawing this thing again and again will help you to remember this thing very easily. So these both small segments are N plus in region. Okay, we have this P minus region. This is gate terminal, and we have applied the voltage here, which we called as VGS, okay. And here VGS is what, greater than 0. Last time VGS was less than 0. Now here VGS is greater than 0, and we have shorted the body terminal, and that was applied with the 0 volt. And as here we have VGS greater than 0, so the grounded portion will be at lower potential and the gate terminal will be at higher potential. So the electric field's direction is what, always from higher potential to lower potential, and this will be the direction of electric field, okay. So again the positive charge will be attracted towards the lower potential, and here, as the positive charge left this area, here we will left with the negative ion. Okay, and these ions are immobile, they can't move. Okay, negative ion, and these are what? Positive charge which moved from upside to downward, and the left is what? Negative ion. And the ions are immobile, they can't move. Okay, as we have immobile ions between source and drain, terminals, no current will flow and the MOSFET will be in the off condition. Okay, so MOSFET is still in off condition here. So this is what the case 2. And this mode is what we call this mode as depletion mode. Okay, now we are moving to the case 3, and in case 3 what will happen here, that VGS will be greater than 0, but this time it will not be a small value, it will be large positive value. Okay, so here the large positive value means greater than the threshold voltage of the MOSFET. Okay, in case 2 we have applied a small positive voltage, but that was below the threshold voltage of the MOSFET, and in case 3 we are applying a large voltage of VGS, and that will be greater than the threshold voltage of the MOSFET. Now again I am drawing that view. This is what? Metal. After that we have silicon oxide layer. The shaded area is what? Silicon oxide layer. Then we have semiconductor part, and this is what? N plus region. This is also N plus region. Okay, N plus region and N plus region. Now at the gate terminal we have applied a voltage, that is what? VGS. Okay, VGS, which is what? Greater than 0 here. So what will happen? This is what? Positive. So the negative charge will be attracted towards this terminal and will be accumulated here, and the positive ions will be left here. Okay, the positive ions will left here. The same phenomena which was happened in case 2, but this time negative charge is attracted towards the positive terminal. Now I am drawing the base. And here we will have a negative ions like this, and there will be some borrowed electrons from the N plus region due to this large positive value of VGS. Electrons are mobile, they can move, so this can be the reason for the current between the source and drain terminal. So now we have a mobile carrier which will be responsible for flow of the current between source and the drain terminal. Now the MOSFET is on. And this mode is called as inversion mode. Okay. So one more thing I want to tell you here. When goes MOSFET goes into case 3, after the case 2, okay, after this condition, at that point VGS is greater than some definite voltage value, and that voltage value is what? Threshold voltage. Okay. That voltage value is called threshold voltage of MOSFET.